Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Math 3, Differentiation, Part 2, Implicit Differentiation. Now, let's first talk about what implicit means and then we'll jump right into it. Before in Pure Maths 1, when you learn differentiation, y was already the subject of the equation. And so it was like something like this. Y equals x squared plus 5x minus 4. This is called explicit, meaning it's very clear. Y is on this side, x is on that side, and it's distinct. So that when you do the derivative, we didn't even keep track of the differentials. All we did was use this y prime notation and then put 2x plus 5. And then if we wanted to find the slope at a particular point, we would evaluate it for only the x coordinate because there's only x variable here, and we plug it in and we could find the slope. This is an example of an explicit equation where it's very clear y is on one side and all the x's on the other. When we get into implicit differentiation, we're going to get into a situation like this that we're going to look at in a minute, where your x's and y's are all mixed up. In fact, sometimes they're even combined in the same term. So explicit means it's very clear. Implicit means it's implied, it's in there, but you gotta kind of bring it out. So that's the kind of differentiation that we're doing, implicit differentiation. Because the x's and y's are mixed up, you have to keep track of the differentials. In other words, every time you derive an x term, you need to put dx at the end. Every time you derive a y term, you need to put dy at the end of it. And you need to keep track of those dy dx's. Then we'll separate them out towards the end and then get the dy over dx for slope. You did that a little bit in Pure Maths 1 with changing rates, and you would keep track of the differentials, like maybe how does the volume change of volume, or how does the volume change with respect to how the radius of a circle changes or of a sphere. So you did a little bit of it, but now it's going to be a little bit more complex, and now you have the product and quotient rule, mainly the product rule, to implement as well as we go through this. So let's look at our first question here, and it says, find the gradient of the curve x cubed plus 3xy squared minus y cubed equals 1 at the point with the coordinates 1, 3. So this right away you should recognize as implicit differentiation because your x and y variables are all mixed together. So that's kind of your clue to not try to do a shortcut with just y prime or starting off right away with dy dx, but to keep track of those differentials all the way through and make sure you execute the derivative rule correctly. So what we have here, we have our original equation, x cubed plus 3xy squared minus y cubed equals 1, and we're going to differentiate it. So this first term is just your normal algebraic differentiation. You multiply the exponent to the front and you subtract 1 from the exponent. And because we're deriving a term with x in it, we put the dx, the differential, at the end. So this one is pretty straightforward, same thing you did in the Pure Maths 1 book with algebra. Now we move on to this term here, and we notice that there are two different variables involved. And so this is like a product. There's a product of 3x and y squared. So this is where our product rule comes into play. And remember, the product rule is 1d2 plus 2d1. The formula is in your formula sheet if you need to follow in the formula sheet. But 1d2 plus 2d1. So here's the 1, the 3x, times the derivative of 2. So multiply the exponent to the front, subtract 1 from the exponent, and since we're deriving a y term, we now put dy as our differential. So here's the 1d2 plus, now the 2, the second part of the term is y squared, and then d1. So the derivative of 3x is 3, and since we're deriving an x part of the term, then it's dx. So don't forget the dx. 3 dx is the derivative with the differential. And then we have another algebraic term here in the back, and it has y as the variable. So multiply the exponent to the front, gives you -3. Subtract 1 from the exponent gives you 2. So you have a -3y squared, and since y is the variable, we have dy as the differential. And then on the right hand of the equation is a constant. Don't forget when you derive a constant, it becomes 0. So don't just put equals 1. Don't forget you're deriving the right hand side as well. And the derivative of a constant is 0. There was no variable in it, so it does not get a differential. Okay. Now that we've done the implicit differentiation and kept track of the differentials, now we're going to start separating out our dy's from the dx's. But first, let's simplify it first because we have some multiplication in here. So we get 3x squared dx. Here's 2 times 3 is 6xy dy. And then here we have a 3y squared dx. And our minus 3y squared dy equals 0. So we just simplified it a little bit. Now we want to separate the dy's from the dx's. We're going to put all the dy's on the left and all the dx's on the right. So notice this is a dx term. So we don't want this on the left. Here is our first dy term. So 6xy dy. This is a dx term, this is a dy term, so minus 3y squared dy. So we put the dy's here together on the left, and the dx's we're going to move to the other side, so we need to subtract this over, and we get a minus 3x squared dx, and then this one also subtracts over and becomes minus 3y squared dx. So again, notice you are not separating x's and y's. You are separating differentials. You're separating the dy's and the dx's. So notice this is a y, but it's with a dx. Okay, and notice here's an x, and it's with a dy. So you're separating the differentials, not the variables. Now, once we've separated the dy's and the dx's, now we can factor out the differential. So here we have our 6x minus 3y squared and factored out the dy. The dy is common to both. Here the dx is common to both, so we factor it out and we get negative 3x squared minus 3y squared with dx as the differential. Now that we have the differentials factored out, now we can set up our slope. We know that slope is dy over dx, change in y over change in x. That's what the differential represents, a change. So the change in y over the change in x, we just divide the dx to both sides. It cancels on this side. So divide dx both sides. Cancels on this side. So we get dy dx. We divide this expression here, the 6xy minus 3y squared. We divide that to the other side. And so what we end up with is a negative 3x squared minus 3y squared on top, divided by 6xy minus 3y squared on the bottom. Be careful that you don't make hasty simplifications. Some students get to a place like this and they see the 3y squared on the top and on the bottom and they cancel it out. Or they see a 3 top and bottom and they cancel it out. And you just can't take 1, 3 like this and cancel it out. This is division, and these terms are separated by add or subtract. Division does not undo add and subtract. So you cannot cancel in this particular form. However, you can divide top and bottom both by -3. And -3 divided by -3 is 1, which means we're not changing the value of the fraction. We can divide the top and bottom by the same value to reduce. You can reduce it that way. It's really the same thing as factoring out the -3. Remember, factoring is division. You're factoring it out if you want to do it that way, and then canceling the -3. So this is just a different way of showing it. So factor and cancel, or just divide top and bottom by -3. So -3 divided by -3, that just leaves us with x squared. And -3y squared divided by -3 changes it to a positive y squared. So think through it carefully. 6 divided by -3, that went in the back. We put this one first since it would be positive. -3y squared divided by -3 is positive y squared. That's why I put it in the front. Don't usually like negatives to lead off in a fraction. So it gets a little confusing whether the negative goes to the whole fraction or just the top or bottom. So generally we try to avoid it like this one up here. These negatives are inside the fraction, not outside. Then 6 divided by -3 is -2. So we have -2xy. This now is a little bit more simplified, and we want to evaluate it. These bars that I drew here means that you're evaluating it for a particular value. Now in P1, you only put in the x coordinate because there were only x variables in your derivative. Now there's both x's and y's mixed up because this is implicit differentiation. They're all mixed up. So you get both x's and y's in your slope formula. So that means we need to plug in both the x and the y into these spots here. So you can there's a couple ways you can do it. You evaluate it. You can either put it in as a coordinate like I did, or you could write it separately, x equals 1, y equals 3. Doesn't really matter as long as you're communicating what you're doing and what you're plugging in for your evaluation. So we plug in the 1 and the 3 in for the x's and y's, make sure the 1 for the x and the 3 for the y's, and we get 1 squared plus 3 squared, which is 1 plus 9 on the top. And then in the denominator, we have 3 squared minus 2 times 1 times 3, or 9 minus 6, and our slope comes out to 10/3. So this now is the answer to this particular question. Very similar to what you were doing in Pure Math 1 as far as derivative, its main application being slope. But now you're applying like the product rule. You now have to keep track of the differentials. So you need to be a little bit more careful on your mechanics of working it out, your execution of it, pay close attention to that. But most of it is just algebraically working it through until you get the form that you need, and then plug it in and simplify. Okay, so that's what we're doing. And I've got a few other examples to set up for us here. Okay, let's look at our second problem here. And again, if you're interested in the code, it's up here, so you know where to find it. The equation of a curve is x squared times parentheses x plus 3y minus y cubed equals 3. Show that dy dx equals x squared plus 2xy all over y squared minus x squared. Now, usually when they take implicit differentiation and make it a show problem, it's usually the first part, and then they want you to do, a follow-up to it. So we'll look at the follow-up a little bit later. And the nice thing about that is, in case you can't show it, you still have your starting point for the second part of the question. But let's do the show part. Let's go back to the board. Here we have our equation up here, and this is what we are supposed to show over here. So at least it helps you in case you make a mistake, you can kind of go back and figure it out, and hopefully you don't take too long on it. But the first thing that we want to do is to do the differentiation, keeping track of differentials. You should recognize this first looks complicated. It's a product rule. So you have an x squared times the parenthesis acts kind of like a term by itself. So we have the x squared term multiplied by the parentheses, and we're going to use the product rule. So 1d2 plus 2d1. Don't forget the rule. It's in your formula sheet. So 1d2, x squared is the first term, then the derivative of the parenthesis. So the derivative of x is 1 dx. Don't forget the differential. Then the derivative of 3y is plus 3 dy. Again, don't forget the differential. And then plus 2, here's the second term, the parentheses, d1, which is 2x dx. Then we move over here to this other term and just do the algebra rule here. So we get minus 3y squared dy, and don't forget that your derivative of a constant is 0. Now we want to distribute and just kind of simplify what we have here. So we distribute the x squared through, that gives us x squared dx plus 3x squared dy plus 2x squared dx and 6xy dx minus our 3y squared dy equals 0. We've now simplified out that. Now what we want to do is to separate the differentials, the dy's from the dx's. The dy's on the left. All the dx's will move to the right side of the equal sign. So here is a dy and here is a dy. So 3x squared minus 3y squared, parentheses with the dy factored out at the end. And then all of these other ones are dx's. Notice these two are like terms. So we have an x squared and a 2x squared. That's 3x squared that we're moving to the other side. So minus 3x squared and a minus 6xy with the dx factored out at the end. Then divide both sides by dx. Cancels on the right and shows up on the left, dy dx. We divide this parentheses here to the other side. So we end up with a negative 3x squared minus 6y divided by our 3x squared minus 3y squared. Again, we notice that there's a common factor of 3 in here, and we want to get rid of these negative signs as much as we can. So we're going to divide top and bottom by negative 3, or if you choose to do it by factoring the negative 3 and then canceling them out, you can do that. So negative 3 divided by negative 3 gives us a positive x squared. The negative 6 divided by negative 3 gives us a positive 2xy divided by, and because this term becomes positive, we'll put it in the front. So we get a positive y squared minus the x squared. This then is the differential that they wanted us to find. So we were able to show the slope by doing implicit differentiation. Now let's go back and look at the second part of the problem and see what application we're supposed to do with it. Okay, the second part of the question says, hence find the exact coordinates of the 2 points on the curve at which the gradient of the normal is 1. So find the exact coordinates. So exact means, again, no decimals. Coordinates, plural, that means both the x and the y coordinate of the 2 points, so there's going to be 2 sets of coordinates from the curve at which the gradient of the normal is 1. Okay, so let's go back to our board. It says that the slope of the normal is 1. Therefore, because tangent and normal are perpendicular, the tangent slope is -1. Just the negative reciprocal of 1 is -1. Why do we want the tangent? Because the slope of the tangent is the same as the slope of the curve at that particular point. So we convert from normal to tangent by doing perpendicular slope. And then this is what we set equal to our derivative because those 2 slopes are the same at that particular point. So we have this, then just multiply the denominator to the other side. And that gives us x squared plus 2xy equals, multiply this -1 here times these. So that's a positive x squared and a negative y squared. And then when we subtract x squared from both sides, that cancels out on both sides. Add the y squared over, so we get y squared plus 2xy equals 0. Now be careful at this point. I notice a lot of students, when they get here, they'll try to divide y to both sides to cancel this y. Don't divide out a variable that you're solving for because it will eliminate one of your answers. So never divide by a variable that you are solving for. If the variable is not something that you're solving for, it should be okay to divide it out, but don't divide out a variable that you're trying to solve for. So since we're solving for both x and y, you don't want to divide out the y, we'll lose a solution. So instead, get everything onto one side and set it equal to 0. So we add the y squared over, y squared plus 2xy equals 0. Now we factor out the y instead of canceling it by dividing. We factor it out, y times y plus 2x equals 0. Set both of those factors equal to 0. You get y equals 0. And then when you subtract 2x to the other side, you get y equals -2x. So notice if you had divided by y here, you would have eliminated the y equals 0 solution. So be careful not to do that. So now we have 2 values for y. And when you're looking for coordinates, then you need to plug those values back into the original equation. So when we plug 0 back in here for the y, that just leaves us, when we plug 0 in for y, these go away, and that just gives us x cubed equals 3. And then we want to cube root both sides to get x by itself. So x equals the cube root of 3. Remember, it wants the exact answers. So don't change that to a decimal. Just leave it as the radical. And so point 1, one of our points is going to be the cube root of 3 and 0. Now for the other one, we're plugging in a -2x for the y. So when we plug in a -2x here, that gives us a -6x. Okay, we're plugging in a -2x, so that's a -6x plus x gives us a -5x times x squared gives us a -5x cubed. So a -6x plus x is -5x. -5x times x squared is -5x cubed. And then when we plug in a -2x in for that one, a -2 cubed is a -8. So that gives us a +8, and then x cubed for that. So a +8x cubed. Don't forget, when you're cubing a negative, it is still negative, times the minus sign in the front makes it positive. So 8x cubed minus 5x cubed is 3x cubed equals 3. Divide both sides by 3. X cubed equals 1. And then cube root. and the cube root of 1 is still 1. So x equals 1. Now we need to plug that back in because we didn't have a numeric value for y. And so we plug 1 into here for the x, and we end up with -2 for the y. So our point now is 1, -2. These are both coordinates of the 2 points on the curve that have a normal gradient of 1, meaning a tangent slope of -1. So that was our second example. We've got a couple more lined up for us. Okay, for our next problem, let's take a look at it. Here again is the code up here, W19, Winter 19, paper 32, number 5. The equation of a curve is 2x² minus xy² equals a cubed, where a is a positive constant. Show that there is only one point on the curve at which the tangent is parallel to the x-axis, and find the y-coordinate of this point. And notice it's 7 points for this question. So you have about 10 minutes to work it out. So just, slowly work your way through it. Let's go back to the board here. Actually, it's not as difficult as what it looks. You do have to make a few connections though, correlate a few things. So notice it says that the tangent is parallel to the x-axis. The tangent, remember the tangent has the same slope as our curve at the point that we're looking at. So if the tangent is parallel to the x-axis is like this, meaning the slope is 0. So we have 0 slope that we're working with. Find the y-coordinate. So we need to make sure that we find the y-coordinate. And it also says that a is a positive constant. So don't forget little statements like that. Usually when we first read a question, we don't really understand why they say that. We see the a cubed in the equation, but we don't really understand the significance of the statement. That's why as you get towards the end and you start getting solutions, you need to come back and revisit little statements like that to see if it affects your solution set. So also, when we look at our equation, we notice that now we have 2 products. We have a product in this first group here, and we also have a product in the second group. So that means we're doing the product rule twice. So let's get started here. Remember 1d2 plus 2d1. So I always put the coefficient with the first part. So 1 is the 2x². Then d2, don't forget the differential. So it's 1 dy plus 2. The second part is the y. And then d1 is 4x dx. And then we go right into a product rule again. So 1 is the negative x, d2 is then 2y dy plus 2, which is y² d1, -1 dx. So don't forget the negative, the sign goes with the term, and also don't forget the differential. So -1 dx, and because a is a constant, then the derivative of a cubed is 0. Don't put 3a² dA. A is a constant, and the derivative of a constant is 0. Then we just need to multiply out these parentheses, multiplication. So we get 2x² dy plus 4xy dx minus 2xy dy. And here's a negative from our derivative, so a negative y² dx equals 0. Then we want to separate out the dy's from the dx's. So the dy's we want to put on the left, the dx's we want to move to the right of the equal sign. So I just pointed out our dy's here. Remember, it's dy's. Don't look for the y's or the x's. You're looking for the dy's and the dx's. So here are the dy's. So 2x squared minus 2xy, factored out the dy on the left. Then on the right, we want to move the dx's over, so we have to add that to the other side. So there's our y squared. We need to subtract this one, so minus 4xy, and then we factored out the dx. So the dy is on the left, the dx is on the right. So then we can divide both sides by dx. Cancels on the right, ends up on the left, dy dx equals, and then divide this parenthesis over to the other side. So I have y squared minus 4xy divided by 2x squared minus 2xy. This is our slope. Our slope is our slope of the curve is equal to the slope of the tangent line at the point we're looking for. And it says that our tangent is parallel to the x-axis, meaning the slope is 0. So we set our derivative equal to 0, and we need to solve for it. So this whole bottom part just cancels out, multiplies into the 0, becomes 0. So we have y squared minus 4xy equals 0. Then factor out a y. So y times y minus 4x, because there's a y common to both terms. And now it's the product, the 0 product rule. So that means either y equals 0 or y equals 4x when we add 4x to the other side. So if we take notice, I've thrown out the y equals 0. Now, why did I say y cannot equal 0? Well, if we plug 0 in up here for the y's, this term becomes 0 and this term becomes 0. And so 0 equals a cubed, which means a would also be 0. But that goes back to the statement here. It says that a is a positive constant, meaning it is not 0. So if a cannot be 0, this is not the solution it's looking for. So it gets thrown out. So y equals 4x. So now we put 4x in for the y. So 4x here, 4x here that's being squared. So 4 times 2 is 8. 8x cubed. We get here. Here we have 4 squared is 16. X squared times x. So we get a negative 16x cubed equals the a cubed. So we're working with our original formula. 8x cubed minus 16x cubed is a negative 8x cubed. Divide by negative 8. So we have a negative 8 cubed over 8. Cube root. Remember, cube root of a negative is still negative. Cube root of 8 is 2, and cube root of a cubed is a. So our x value is a negative a over 2, but it wants the y value. So we need to plug that back in over here into our y equals 4x. So that gives us y equals 4 times a negative a over 2. The 2 and the 4 cancel, giving us y equals a negative 2a. This is actually the answer that it wants, the y coordinate. So y equals a negative 2a. And I just put it up here as an ordered pair. Our point is at a negative a over 2 for the x coordinate and a negative 2 times a for the y coordinate. So again, a lot of what you're doing is just algebraically working things through, using derivative, the product rule, keeping track of your differentials. But there are also some correlation things that you need to remember from Pure Maths 1 and from the different applications that we did with derivatives. So again, you have about 10 minutes to do this particular question. So take your time, and if you work slowly and carefully on your mechanics, again, you should end up with a good result. And actually 10 minutes, you probably still should have a minute or two to spare with this particular one. Got one more example for us for this video. Okay, here is our last question for this video. And it says, again, you see the code up here. The equation of a curve is 2x cubed minus y cubed minus 3xy squared equals 2a cubed, where a is a non-zero constant. Show that dy dx equals 2x squared minus y squared over y squared plus 2xy. So again, this is a two-part question, but first let's do the show part. Okay, here we are. Here's the equation that we were given, and this is what we are supposed to show. So this is the end result that we want. So notice we look for those products. We have a product right here. These other two are just normal algebraic terms. So when we do the derivative, we just get 6x squared dx minus 3y squared dy. Now here's the product. So 1 and negative 3x d2 times 2y dy plus 2d1. So here's the 2 term, the second part of the term, y squared, and the derivative of the first. Again, remember the sign goes with the term. So a negative 3 dx, don't forget the differential. And since a is a constant, the derivative of the a term is 0. Then we just clean this up by multiplying in these parentheses. So we get 6x squared dx minus 3y squared dy minus 6xy dy minus 3y squared dx equals 0. Now we identify our dy terms, keep them on the left. We'll move the dx terms to the right. So we have a negative 3y squared minus 6xy times factored out the dy. And then to the other side, we're going to move our dx term. So this one becomes positive 3y squared minus 6x squared. Factor out the dx. Divide dx to both sides so that it cancels out over here. And we end up with dy dx equals 3y squared minus 6x squared in the numerator. Divide this parenthesis over to the other side, giving us a negative 3y squared minus 6xy in the denominator. And as we look at this compared to what it's supposed to be, we can divide top and bottom by negative 3. And that will make this one positive 2x squared, makes this one negative y squared, all over positive y squared plus a 2xy. And so we have shown that we can arrive at the form that they wanted us to. So we've done our implicit differentiation and we've got the slope as the result. Now we need to look at the second part of the problem to see what application we need to do. The second part of our question says, find the coordinates of the 2 points on the curve at which the tangent is parallel to the y-axis. So find the coordinates, so both the x and y, of the 2 points, so 2 sets of coordinates, at which the tangent is parallel to the y-axis. Okay, so we come back here. Here's our original equation. We already showed that the derivative is this. So it wants us to find the coordinates, plural, that means both the x and y, of 2 different points at which our tangent is parallel to the y-axis. Now remember, a is a non-zero value, and our tangent has the same slope as the curve at the particular point of tangency. So this slope is same as tangent, and this is parallel to, again, parallel means same slope. So the curve has the same slope as the tangent, and parallel means it has the same slope as the y-axis. Well, your y-axis is running up and down, and a vertical line has an undefined slope. How do you get an undefined slope? You get an undefined slope when you divide by 0. You can't divide by 0 But when you're rise over run, you have all rise, you have all change of y, but you have no change of x. There's rise, but no run. And so this is called undefined slope because we can't divide by 0, which means that the derivative, or sorry, the denominator of the fraction is equal to 0. When the denominator of the fraction or of this derivative is equal to 0, then that causes an undefined slope, which will be parallel to our y-axis. Okay? So we want the y squared plus 2xy equals 0. This is application and correlating information that you have learned in the past. So here's the equation that we're working with, y squared plus 2xy equals 0. Factor out a y that's common to both. So using our 0 product rule, y equals 0 or y equals a negative 2x. When we plug in the 0 into the original, we just end up with 2x cubed. That's 0 equals 2a cubed. Divide both sides by 2, x cubed equals a cubed. Cube root both sides, x equals a. So our first point is a and 0. The coordinates of the first point, the x value is a, the y value is 0. When we plug in a negative 2x, we still have 2x cubed for this first term, a negative 2 cubed. That becomes a negative 8. Negative 2 cubed is a negative 8 times the negative makes positive 8x cubed. So a positive 8x cubed. So be careful of your signs, especially if you're using the calculator to help you. Make sure you put the negative in the parenthesis and the exponent on the outside of the parenthesis if you're using your calculator. So that's a negative 8x cubed times the negative in front makes it a positive 8x cubed. Then we have another negative 2x that's being squared. So that gives us a positive 4 times a negative 3 is a negative 12. And an x squared times x is x cubed equals the 2a cubed. So 2 plus 8, these are all like terms. 2 plus 8 is 10. 10 minus 12 is a negative 2x cubed equals 2a cubed. Divide by negative 2, x cubed equals a negative a cubed. Cube root, remember cube root of a negative is still negative. 3 negatives make a negative, so x equals a negative a. We need to plug that into our y equals negative 2x because we still have the variable there. Plug in the negative a, and that gives us y equals a positive 2a, so that our second point is a negative a and positive 2a. Here are the 2 points on the curve that have this slope, which is also parallel to the y-axis. So that concludes our examples for implicit differentiation. Thank you for joining me in the Zoom room and hope to see you again next time.